Today, we're going to start talking about the details in calculus. And we're going to start with limits and continuity in the other order. We're going to do this law and order sign. We call it law and order, and then they show the past. They show the police first after the word law, and then order for the lawyer, and that's backwards. Right? The police are more the order part, and then the lawyers do the law part. So, law and order, if you're listening, the attorney should go first. It's not chronological, but you're the ones that called the show law and order and not order and law. So, of course, what leg have I got to stand on? Limits and continuity. I want to talk about continuity. We're going to start with an intuitive idea about what continuity is. And then we're going to realize that it's not a very good description. So sometimes we say that a function is continuous if we can draw its graph without lifting our pen from the paper. This is a bad definition of continuity, but it works really well. So a function is continuous if we can draw its graph So this is kind of a bad description of continuity. It's not very mathematically rigorous. Kind of bad description, but it's a decent enough introduction. What we're looking for is a graph with no breaks or jumps or holes. We want a graph that has no jumps or holes. So we're going to talk about what is a continuous function by looking at what is not a continuous function. They're going to have a discontinuity. That is, they'll be discontinuous at a point. That was a lot of terminology flying at you right away. Here's an example of a function that is discontinuous. Tell me where this function is discontinuous. At 1. If you try to plug in 1, this function is undefined. This function is undefined at 1. Try to evaluate this function at 1. You don't get any. You get 0 over 0. That's not defined. So the function is discontinuous when x equals 1. You might say f is discontinuous at x equals 1, or when x equals 1. Let's see what this looks like in terms of a graph. I picked this because it's really easy to simplify. We can bust out our mad algebra skills, factor the numerator, and cancel out the x minus 1. And so we get this equation. Is this equation true? I like your suspicious nature. Is this equation true for all x? No, why not? Because of the whole. We just said that f is discontinuous at x equals 1, but x plus 1 on its own is not. X squared minus 1 over x minus 1 is not always equal to x plus 1. These expressions are not equal when x is equal to 1, because the first expression is undefined and the second expression is 2. This is only true for x not equal to 1. But what this means is that we can use the graph of x plus 1 to visualize the graph of x squared minus 1 over x minus 1 everywhere but 1. So we end up with this line with a hole in it. That fits with our intuitive description of continuity. To draw this graph, we had to lift our pen off the paper so we could jump over that point 1. A lot of times we'll use a small circle to emphasize that there's a hole there when we're drawing graphs. So we can use a small circle to indicate that there is a hole. But that point is not there. This function is discontinuous at x equals 1. You can't be like, oh, well, I can draw it by like going up here and then going around the circle and then just keep going on. I never lifted my pen off the paper. Yeah. And I say it with that disparaging tone because you know what I meant. It's like when a kid says, can I go to the bathroom? The teacher shouldn't be like, oh, I don't know, can you? Because the boss response to that is to be like, oh, yes, then get up and just walk out. Or if you really want the big move, yes, apparently I can. And we get a cleanup on aisle 3. That would be the super move. But anyway. Anytime a teacher tries to pull that on you, just say, oh, yeah, yes, I can. And then get up and go. Incidentally, don't ask, just go. We're adults. Ultimately, because get up and just leave campus if you want. I'm not going to stop. What am I going to do? You make it to the door and leave you? I know some of you have been like right out of high school. You got taste and trying to leave. So this is one type of discontinuity. There's a hole in the graph. Graph goes along, has to stop at this one point where it's undefined, but then it just keeps going on. Here's a piecewise defined function. We have a line moving up to 0, and then it switches to a parabola afterwards. Now we can see that this line does not end where the parabola part begins. When x is equal to 0, x plus 1 would be ending at 1, from your perspective. But then the parabola is going to be down here, 1 unit lower, and then go up from there. So what we're going to see in the graph here is a line up to, but not including 0, and then drop down here and pick up again for the parabola part. There's a hole that indicates the graph is not, the line doesn't end at 0. It ends before 0. And then the x equals, the vertex of the parabola is filled in because that's where the function is actually defined. So there's a jump discontinuity. Jump. Any questions? Just because the function is piecewise defined does not mean that it's discontinuous. And if I had instead the function g of x is equal to x for x less than 0, and x squared for x greater than or equal to 0, that would be a continuous function because the line would stop at the vertex of the parabola, and then the parabola would you just draw a line up to 0, then start drawing a parabola. That's all connected. That's continuous. You would like to note that where the equal sign is, that's how we plug in the 0. So g of 0 is equal to 0 squared, or 0. G of right before 0 will be right before 0 plus 1. But g of 0 is just for 0. Remember that for functions, we can't have one input giving us 2 outputs. To be a function, each input can correspond to exactly 1 output. Any questions? So that's just the example I spoke. So just because something is a piecewise defined function doesn't mean that it's going to be discontinuous, but it does kind of indicate where to look first for the discontinuity. Other kinds of discontinuities that we can have, other breaks or jumps. Q of x equals 1 over x squared is discontinuous at x equals 0. It's undefined and undefined in a very messy way. The value of 1 over x squared goes to infinity as x gets closer to 0. So this function is discontinuous in a very messy way. The function goes to infinity when x is equal to 0. There's a vertical asymptote at x equals 0. How's everybody? Just like a friggin' math class. Define this term. Let me show you all the things that's not that thing. Can't you just define the thing? Yes, but it's kind of messy. And we need the other part of this discussion, which is limits. So to define continuity rigorously, we need limits. Question? Today was a lot of me, blah, blah, blah. Tomorrow there'll be a combination of me, blah, 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 and you, right. And you will also be against the blah, blah, blah at each other. So I even put the roll sheet out. I'll try to remember tomorrow. All right. So tomorrow we're going to talk about limits. That should be kind of obvious from where this left off. So tomorrow we'll talk about limits. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.